Good morning, good afternoon, everyone. As I said before, this lecture is going to be done using the iPad. So what you'll be seeing is the actual screen as opposed to the projection, as we've done for some other lectures. Anyway, so let's jump right in. I'd like to start off for 1 second talking about the end of last lecture and what we discussed. So we went over a couple of examples, which you can see here. We still haven't gotten to the point of actually solving problems, although actually I think we did solve one up here. And when I say solving, I mean calculating the voltage or current within a circuit. But we did solve one actually. However, we also spent some time looking at more complex circuits and writing out the equations, the relevant expressions for them. I think the example I'm really focusing on here is this example, where we had a relatively complex circuit and we spent some time writing out the KCL, Kirchhoff's current law expressions for that circuit. And that's really an important part of this class, is not only understanding how to solve. Obviously you need to be adept in manipulating the equations using algebra, etc., etc. But the new part of this course is the ability to observe, to examine the circuit, to make any appropriate simplifications, and then write out the expressions that are needed in order to solve. All right, so let's jump into new material. This is lecture number 3, and we're going to be simply continuing with some of the chapter 2 material. All right, so let's jump into another example. And it asks us to solve, and I'll draw the circuit in a second, for two values, VAC and VEC. Now, I think this example is going to touch upon some concepts that you have already seen in your homework. I did tell everybody to sort of approach the homework slowly, to stick to the beginning of Chapter 2 homework, but I've gotten some questions on stuff later on. And what we're going to talk about now is the sign convention, or the naming convention for voltages. So let's say that we have two different voltages, VA and VB. Then we can note that the difference between them, which we'll call VAB, that is the exact same thing as saying VA minus VB. And so this is going to be our dual subscript naming convention. Now, you'll often see a single subscript naming convention, and that will be used when we're referring to ground or referring to a neutral. So, for example, let's say we have a voltage VA, and I'm going to call N the neutral. We can often call that simply VA, and that is equal to VA minus the neutral, or the ground voltage. Now, which voltage in the circuit is the neutral or the ground? That is going to be dependent on the problem that we're looking at, and will normally need to be defined either by you or by the problem. Okay. So next, let's draw out the circuit that we're looking at. It will take me a second to draw this out. It's a little bit of it has several parts. So we have a voltage source. We have a resistor. And now you can start to see that there are components in this class that we are going to see over and over again. We haven't talked about dependent sources explicitly yet. We also really haven't explained what a current source is. However, voltage sources, current sources, resistors, and then later other capacitive elements like capacitors and inductors are going to be pretty commonplace here. And these all make up our definition of linear circuits. All right, so let's label these guys. This is called R1. This is called R2. This is called R3. And this is called R4. This I'm going to call VA, which is 24 volts. You know what? VA is not a good name for that. Forget it. This is 12 volts, and that's it. Now, they give us the voltage across some of the elements. It's defined for us already. So this is a 4 volt difference here, here. This is a 6 volt difference here, here. This is a 10 volt difference here. I didn't write my V. 10 volt difference here, here. And then 16 volt difference here, here. Okay, so that gives us all the voltages in the circuit. I never defined the nodes. This is node A, this is node B, this is node C, this is node D, this is node E, and this is node F. Now, what are they asking us? They're asking us for two voltages, AC and EC, right? So what is voltage AC? Voltage AC is going to be voltage A minus voltage C. So VAC is going to span from this point to this point right here. Then we have voltage EC. That's a C. Okay. And that's going to span from this point here to this point down here. Now, are my polarities right? I know you can't answer me, obviously, but the answer is not for the second one. No, it's not right. When we say VAB, that implies that our polarity looks like this, VAB. VA minus VB. Hence, down here when we have VAC, it should be positive, then negative. And this should be positive, then negative, because it's VE minus VC. So, those are the definitions of the two values that we're looking for. Now, let's jump in to solving. First thing we're going to do is we're going to solve for the first value, solve for VAC. And in order to do this, we are going to imagine, so for this, we will imagine a black box or some sort of other source replacing the label above. So I'll show you what that means. So we will imagine another element replacing the spot where VAC lives. All right, so let's see what that means. So VAC lives in this area right here, right? It lives here. So what we're going to do is we're going to redraw the circuit now with those two elements replaced with essentially like a black with a box. We use the term black box, but not really relevant here. Okay, so we have to draw the rest of the circuit. So let's do this. All right, we're going to have our node A. The other parts of it are still going to stay the same. So we still have our 24-volt source. This here is going to be our VAC. Okay, we have our R4. So this is node F, this is node E. We still have R3. And we still have R2. And we still have our node C. Okay, the rest of this is gone though. Okay. And node B is no longer going to be an evident part of the circuit because that's included within the box. Real quickly, let me write out the values. I know that a lot of this is redundant, but I do want to give you all the information on this new circuit. And again, I know this is not the fastest way to handle this type of problem. I'm sure many of you could eyeball this or do this much more quickly, especially after you've gone over the homeworks. However, my methodology here for the lectures, for better or for worse, is pretty much always going to be to do it in the most fundamental manner possible, meaning showing every single minuscule step along the way. Has its pros for certain students, has its cons for certain students, but at least it provides a really, really good resource for those who have questions. And if you want to fast forward here, I wouldn't blame you a little bit. All right. So anyway, now let's calculate what VAC is. And for this, now what we can do is we can just apply KVL here, right? We will apply KVL to this circuit. And so what will that look like? So I will define a polarity for voltage. Well, it's already given to me. Voltage AC has this polarity. And so let's write out KVL. I'm going to assume that VAC has the positive polarity. Okay, so starting from VAC and moving clockwise. So we have VAC minus 4 volts, minus 6 volts, minus 10 volts, and then we have to plus. Sorry here, I made a mistake. 4 volts, 6 volts, and 10 volts all agree with the polarity of VAC. So those are plus, plus, plus. And then it's minus the 24 volts equals 0. So what we do, just use our algebra. So we have 10 plus 6, 16, plus 4 is 20. So 20 minus 24 gives us negative 4 volts here. And then we go ahead and move that to the other side. And what we're left with is VAC equals 4 volts. So, couple of mini steps, sub-steps in here. What we did was replace our VAC, those two elements that are included within it, with a separate box. And then we just applied KVL as we would regularly, and came up with a value of negative 4. Again, that didn't necessarily require us to completely redraw the circuit. And in fact, when we solve for VEC, I am not going to redraw it. I'm just going to go ahead and use the version of the circuit that's shown above. Okay, next, step number 2. And for that, we're just going to try the same thing for VEC. All right. So we want to write out KVL. I took a second to listen to the video, and I'm sorry for all the rustling noise. I'm trying to find a way to hold the iPad such that it doesn't make that, but it's a little bit hard. I don't like sitting on a table when I write. That's really what I need to do. Anyway, if I do this again, I'll try to find a better way to do this. All right, so now VEC is going to contain these two elements. So really what we need to do is just write out KVL for this circuit, replacing those two elements with a box. All right, so let's do that. So let's write out, again, I'm going to start off with, and for this one, I'm going to do it a little bit differently. I'm going to start off with the 24-volt source, okay, the one right here. I'm going to start out with the 24-volt source and use that as the positive polarity. Okay, so 24 volts minus 16 volts plus 12 volts. Again, looking at those two values. So minus 16 volts plus 12 volts. And then we will have here, the next piece will be VEC. Now, if we look at the polarity of VEC right here, we'll see that it opposes the sign of the 24 volts. So that will be a, it reinforces the sign of the 24 volts. So that will be a plus VEC. And then lastly, we will have minus 10 volts. So for that one, we moved a little bit more quickly. We didn't go through and draw the box and do everything. But hopefully you were all able to keep up. So we'll do our algebra here. We will end up with VEC is equal to, so 24 minus 16 leaves us with 8. 8 plus 12 is 20. 20 minus 10 is 10. And then we move that over to the other side of the equals, and that will leave us with a negative 10 volts. Now, if you look up above, what we did was we used KVL, and we took into account all these elements. Probably the easier way to do it would be to do KVL using these two elements. All right, because the black box can go here, and KVL can be done in either direction. They should both yield the exact same value. So let's go ahead and do it the other way. In fact, KVL doing it the other way, I think we can just add these up in our head, right? We know that VEC will be equal to the sum of, sorry, I'm erasing some values here, the sum of this and this. However, the polarities of those two voltages are the opposite of VEC, and so what we'll end up with is negative 4 minus 6, which gives us a negative 10 volts, which is what we ended up with down here anyway. So I could write it out, but I think that we did a pretty good job of explaining it one way, and so we can go ahead and move on to the next step. For this type of problem, and for many different types of problems, there is more than one way to solve. And, that can be a good thing. It can be, and when I say it can be a good thing, I mean that, it's a great way that you can check your work. So if you're doing a quiz or an exam or even just a homework problem and you're unsure of what you're doing, see if there's a different way to solve the circuit, and hopefully you end up with an answer that agrees. All right. So next section is on something called a voltage divider. And this is a pretty cool little circuit that we are going to use a lot. And you're definitely going to use it in your ENG214 lab several different times. So before I write out anything, let me just give a little preview. What does a voltage divider do? It essentially allows us to bump down a voltage. Okay, let's say we have a 12-volt source coming in. We need a 5-volt, let's make it easy, a 6-volt source. What we can do is we can use a voltage divider. In that case, both the resistances would be equal to one another, and that would divide it in two. Okay, so how does that work? Let's again take a look, but let's take a look at the circuit. So pretty simple. You have an input, Vs, okay, which is coming from whatever external source we have. And we have two resistors. We have a resistor that we're going to call R1, and we have a resistor that we're going to call R2. All right? And so the output here is this. This is the output voltage. And in fact, just for the sake of simplicity, I'm going to refer to this as the input. So we have our input voltage, we have our output voltage, and if you were trying to drive some sort of a load, that load would go right here. But for now, we are going to use the ideal case. And in the ideal case, the load is infinite. And so ideally, I'll write ideally above it. Ideally, the load is infinite. And that also means that ideally, IL equals 0, where this is IL. And what this means, in addition to that, if we were to apply KCL at this node, I'll give it a node name, we'll call it node X. What that means is that all of the current in this loop will be the same. So we could call this IX. So the current flowing through R1 will be the same as the current flowing through R2. And I'll go ahead and set up the voltage polarities for these that agree with the passive sign convention. Looks like that, plus and minus. All right. So now that we know what the circuit looks like, how does it work? What expression describes its operation? So we can determine how do we get the proper relationship between V out and V in. Okay, so it's this. So we have V out is equal to R2 over R1 plus R2 times V in. All right, so this is the important expression here. And this expression depends on the placement of R1 and R2. So you can't switch them around, you can't move the load. As one would expect, it's relative to the definitions shown above. This is an under-constrained definition here. And so what that means is there's lots of values that could potentially work and give you the same relationship. So let's say you want to get a step down of 50%. Okay, so you could use 50 over 50 plus 50, right? That would give you 1/2. You could use essentially any value over, as long as the values are equal to one another, R1 and R2, you'll always get a ratio of 1/2. And that's just one example. So when you calculate what your R1 and your R2 values are, you are going to choose one value and calculate the other. So for example, again, you want a 50% step down. You'll choose R1 and you'll say, okay, that's going to be 1 kiloohm, and then you can get your R2 from that. So now there's other ways to step down voltage we're not necessarily going to talk about right now. So what is good about the voltage divider? The main thing is that it's easy to design, build, and implement. Right? You need a quick fix, you need to step down a voltage. This will allow you to do it easily. Now, what is, I'm going to say bad, but let's say less than ideal? It wastes energy. And let's say you are drawing energy from a battery, you need to step it down, and you're concerned about the energy that's stored in that battery and not just wasting it, right? You want to maintain some battery life. This is not the best way to do things, because when the voltage is stepped down from here to here, what's happening physically is that there is, right, energy that's being dissipated here as heat. Okay, and so the voltage is stepped down by dissipating that energy, and that gives you a lower voltage across R2. So, like I said, it's a quick and easy solution, but when we get to more sensitive energy applications where we're more concerned about conserving energy, we're going to want to use something called a step-down converter, which is a power electronic converter, and we won't be discussing that at length in this class. All right. So next, what I want to do is I want to spend 1 second talking about why the voltage divider works the way that it does, and also it's a good opportunity for us to demonstrate that we can derive these equations that are given to us in the text. So let's try to I'm going to ask the question, so can we derive the transfer function for the voltage divider? And well, the first thing that I should maybe ask is, who knows what a transfer function is? Again, can't really get an answer right now, but What's a transfer function? A transfer function is simply a function, one that relates the input to the output. So if we wanted to write the transfer function for any component, that would be our V out divided by our V in, and that would be equal to T of something, whatever our parameters are, which I could call U, or I could use some other variable. In this case, the parameters are R1 and R2. All right, so what is next? We are deriving this transfer function here. So how can we do that? So let me spend a second thinking about this, because there's a lot of different ways to do this. And this is, one example where we illustrate that these problems are not straightforward necessarily, meaning that there's lots of different ways to solve. I mean, I hate to be repetitive, but it just makes it a little bit difficult sometimes, because students come and say, well, I want to know how to solve XYZ problem. What are the steps? And I've outlined basic steps so far, label everything, use passive sign convention, write out all the expressions that etc., etc. But, after that point, sometimes it's just a matter of being able to manipulate the equations and use the basic algebra to solve. So let's take one approach to this. So the first thing that I'm going to do is I am going to try to define V out using our KVL. KCL wouldn't necessarily apply there, and Ohm's law. Now, the reason why I'm going to start off by trying to define define V out, is because that's the main value that we're concerned with, right? We're trying to define V out in terms of V in. So it makes sense to start there. So there's two expressions that we can write for that. Okay, so let's write out V out in terms of KVL. So V out here, if we go around this loop, KVL looks like this. And I'm going to start off with V in, assuming that is the positive polarity. So we have V in minus the voltage across R1 minus the voltage across R2, which is also known as V out, which gives us 0. Or is equal to 0, not gives us 0. Okay, now Ohm's law. Ohm's law tells us that V out is equal to Ix times R2. Note that our direction of Ix does support the passive sign convention. Okay, so now let's take a look at what it is that we need. So I'll rearrange some things here, and what we end up with is, if we try to isolate V out is equal to VR1 minus V in. So what values do we need to get rid of or further define in order to get to this form of a transfer function? V in is fine, because that shows up over here. So we're okay with that. V out is fine, because that also shows up over here. So our problem is the VR1. That's the value that we need to further redefine or break down. So let's define VR1 such that we remove it. Well, and when I say the expression above, I mean this expression right here. All right. So what can we write out for VR1? We could write out KVL, but honestly, we've already done that. It would be that same KVL right here. So that's not going to help us too much. The only other choice we have is to use Ohm's law. And so Ohm's law tells us that VR1 is equal to IX times R1. And so is that helpful to us? Yes, it is. So we can make a couple substitutions here that will help us solve. All right, so let's show what those substitutions might be. So step 3, make substitutions to solve. And also, so make substitutions or combine equations to solve. All right. So let's start off using the highlighted expression. So we know that V out equals VR1 minus V in. All right. Sorry to backtrack for a second. As you can see, I did make a couple changes here. It's always difficult to do derivations like this on the fly, and I wasn't sticking closely to what I did previously in the notes, and I made a mistake, and that caused a little bit of an issue. So what I'm going to do is I'm going to highlight the mistake and then continue with what we're doing. So the mistake was this equation right here. The V out equals V in minus VR1. I had that backwards before, and mistake on my part, which then I continued down in step 3 trying to use that, and it obviously is not going to work like that. Okay. So what I've done is I've actually completed the derivation. What I'm going to do is start from step number 3, walk through it in the same level of detail that I would if I was writing it on the fly here. Okay, so we had our original expression here. We decided to make a substitution using this expression here, and that yielded this version right here. Again, what we're trying to do is we're trying to get this expression into the form of V out over V in. We still have one value that is not useful in our transfer function, and that's IX. So we can take our So we can take our IX from right here, substitute it in down below, and we end up with this new version of the transfer or of the expression, which is shown there. Now what's next? So we have V out equals V in minus R1 over R2 times V out. We want to end up with V out over V in, and therefore it makes sense to multiply both sides by 1 over V in, which you can see here and you can see here. After we carry that through, we end up with the form of the equation as shown right here. And we need to move and so how was this done? It was essentially, right, it was collecting the like terms, because what we'll end up with when we multiply by Vn over Vn is we'll end up with a 1 times V out over Vn, and we'll end up with a negative R1 over R2 times V out over Vn. And so we collect those two together, and that's what gives us the 1 plus R1 over R2. Now we want to move this to the other side, so we have to divide by that, and we end up with this right here, which is 1 over 1 plus R1 over R2. That's a valid transfer function. You can use that form. However, it's not generally the way we like to see things. Normally, we try to simplify such that there's no fractions inside the denominator of an expression, so we can get rid of that by multiplying by R2 over R2 here, and the result is the R2 over R1 plus R2, and that is the version that is right here. So sorry for the little bit of a mix-up there, but that is essentially how you calculate the transfer function for a voltage divider. Okay, what's the next question that we are going to ask ourselves? So the next question that we're going to ask ourselves is how would a load affect the voltage divider's operation? So what we have up here, like we said before, ideally we have a no load condition, meaning that RL is equal to infinity, and meaning that IL is equal to 0. But if you're going to practically use the voltage divider, use it for a real application, you're going to need to eventually hook it up to some sort of a load. So how is that going to affect it? So let's draw our circuit with the load intact. We have our V in, we have our R1, we have our R2. And one thing I'm going to do here, which we haven't really used this so far, is I'm going to, instead of drawing a complete loop, I'm going to just refer both the voltage and R2 to ground. But since they're both grounded, that would imply, right, there's a short between those 2 points right there. And then lastly, now we have a non-infinite load, RL. And then our V out would be here. So the easiest way to examine the operation is to really just redefine our R2 as the parallel combination of R2 and RL. And what that'll give us is a new voltage divider which fits the form that we have up here. Right? I'll draw it real quickly and to the side. What we would end up with is a source, an R1, and an R2 prime. And then from there, we know that V out over V in would be equal to R2 prime over R1 plus R2 prime. Okay, so that works. But we need to define what R2 prime is. And so that leads us to a question that we haven't explicitly talked about yet, and that's series and parallel combinations of impedances or resistances. So the first step is going to be to define the parallel combination of R2 and RL. No question mark. So how does this work? First things first, what are parallel and series combinations? So in a series combination, it looks like this. We have R1, or I'm going to use RA and RB so we don't get confused with our values above. So let's say we have two resistors. We have an RA and we have an RB. These are considered to be in series with one another because they share one common point, and there is nothing connected here at the midpoint, which means that the current flowing through both of the resistors is the same. So what we can do is we can take these two resistors, okay, and let me give these points names. I'm going to call this point C and point D, and we can combine them together into a single resistor with a value of RA plus RB. So that's how it works for your series elements. We don't have series elements in this case. What we have is parallel elements. So parallel elements look like this. Just giving myself some more space. Parallel elements look like this. So these are two parallel elements. We'll use similar naming convention, so I'll call this node C, I'll call this node D, I'll call this resistor A, I'll call this resistor B. The thing that unites or defines parallel combination is essentially, right, that the voltage across both of the elements is the same. So they share two endpoints. The same two endpoints. All right, we call this parallel. Now, how do we combine these two elements together? We could combine them together into a single element, again, endpoint C, our new resistor, equivalent resistor, and endpoint D. And the value would be RA, RB over RA plus RB. So this is the equation right here that we are going to have to use all the way up here. So we know that R2 prime will be equal to R2 times RL over R2 plus RL, according to, right, this expression. All right, so now that we have in this area here, right, all of this area here, this essentially gives us the definition of series and parallel combinations. This is going to be useful outside of this one example, so this is something that you should definitely put into your study materials, is understanding the differences between series and parallel combinations of resistors. This is also going to work for other types of impedances, and how to find their equivalent values. All right, so now step 2 is going to be, let's compare V out over V in for the cases without and with the load. So let's look at how those expressions will change. When we don't have any load, so the no load or the ideal case, what we'll have is V out over V in equals R2, our original R2, over R1 plus R2. All right, then when we have the loaded case, or the non-ideal, our V out over V in will be equal to R2 prime, which we had, remember, defined here, R2 prime over R1 plus R2 prime. We can replace that with, well, we know the expression, but I'll just write it like this. I'll say R2 in parallel with RL and this would ultimately be R2 RL over R2 plus RL. And so what we can see from taking a look at this and this is, first things first, there will be a difference. The non-ideal case, because our R2 prime is not going to be equal to our R2, the ideal and the non-ideal case are going to give us differing transfer functions. So before I move on to the next step, what does that mean? What it means is that in order to get the voltage divider to work as much like the ideal case as possible, where this is the ideal case up here, okay, in order to replicate the ideal case as much as possible, you want to keep your load RL as large as possible, especially when compared to your value of R2, okay? So if R2 is, and you built this voltage divider, for example, so if R2 is 1,000 ohms, then you'll want to try to keep RL much, much larger than that. So I normally say 1 or 2 orders of magnitude, which means that if R2 is 1,000, then you're going to want to make sure that RL is 10,000 or more ideally 100,000. That would be 2 orders of magnitude higher. So for step number 3, what we can do is, well, we've already done it. We'll formulate an assumption for RL as compared to R2. And that assumption is that we must keep RL much, much larger than R2, which I will take to mean 2 orders of magnitude, in order to assume that R2 in combination with RL is approximately equal to R2, which then would allow us to use the ideal behavior of the voltage divider. So this is an important expression right here. It's going to come into play when you're doing your work in ENG214. Now, we keep talking about R2 being large. Why does that make a difference? Let's take a look right here at parallel combinations of resistors and maybe a quick few cases. So what happens if we combine 2 resistors that have the same resistance? Let's say 5 ohms times 5 ohms over 5 plus 5. What does that give us? Gives us 25 over 10, or 2.5 ohms. So it cuts it in half. Now let's try a different case. Let's do 5 times 10 to the 6. So now this is a 5 ohm resistor in parallel with a really, really big resistor. And so what we're going to see is that in the end, so this 5 plus 10 to the 6 is approximately equal to 10 to the 6, right? Because a million is the same as a million and 5. So what we'll have is 5 times 10 to the 6 over 10 to the 6, which equals 5. Approximately equals 5. So this is why we're saying that we want to keep the parallel load resistor, which in this case would be represented by RB. We want to keep it large because the larger RB is, the less or the closer the parallel combination value is going to be to the original. And the more so this assumption is appropriate, that the 5 plus 10 to the 6 is approximately equal to 10 to the 6. The general rule is that any parallel combo of 2 resistors yields a value, an equivalent value, smaller than the smallest original value. What does that mean? If you have a parallel combination of 2 ohms and 1 ohm, you know the parallel combination is going to be less than 1. If you have a parallel combination of 500 ohms and 0.2 ohms, you know the parallel combination is going to be less than 0.2. Whatever the minimum resistor value is of the two, you're always going to have one that's smaller than that, or the equivalent value will always be smaller than that. Okay. The next thing that I want to talk about here real quick So let's try out this. I don't need to draw the whole circuit again because we know what the circuit looks like. So I'm just going to go ahead and write out the values. So our R1 value is going to be equal to 100 ohms. Our R2 value is going to be equal to 100 ohms. And what is the ideal transfer function for this? So V out over V in ideally is going to be equal to 1/2, right? Because you have 100 over 100 plus 100. But, like we said, we're going to be considering a load. So I'm going to say this load is R2 times 10 squared, which is 10,000 ohms. Okay, so let's calculate what the new gain for the transfer function would be and compare it. So we know that the output over the input for the non-ideal case, is going to be equal to our R2 in parallel with RL over R1 plus R2 in parallel with RL. I have those values ready to go, and so R2 in parallel with RL, 100 in parallel with 10,000 is going to give us 99.0099 ohms. So what we're going to end up with is, when we write this out, 99.0099 divided by 100 plus 99.099. And so let me use my calculator real quick to see what that would give us. So now 99.0099 divided by 199.0099. And so the answer is 0.4975. And so we can compare those two values. It's not exact, but it is relatively close. This threshold that we provide right here, like many things in engineering, is a rule of thumb. Different books may use different values. This is what I'm going to suggest. This is what I'm going to ask that you use on quizzes and exams. In ENG212, I'm going to ask that if you're designing a voltage divider and you want it to work, assume to be almost ideal, that the RL value be 100 times larger than the value of R2. All right, so next time what we're going to do is we're going to jump into dependent sources, voltage and current dependent sources. We're going to talk about circuits that have multiple sources and multiple resistors. We've already done that a little bit, but we're going to talk about how we can combine those together. And we're essentially just going to continue along with this bulk of the material, and we'll talk a little bit about the upcoming quiz, which has been moved. I wrote the email to all of you about that. So if you have any questions, feel free to email me. Come by the office hours next week, and I'm always available by phone if you need something. All right. Thank you very much, and I'll see you next week.